So we are ready to do estimating population mean. So we did population proportion. Why do we have to have separate ones for proportion and one for mean? Why are they different? What's the major difference? One's categorical data, the other one is quantitative data. The mean is what? Which one is the mean? Is it category or categorical or quantitative? It is quantitative, right?
I had a
50, 50, 90. It comes again. Go quantitative, right? Because you can actually do an average, and the average has some sort of meaning, right? That's why it's called quantitative, right? Okay. Right. So, from a population, we take a sample just like we did before. So let's do a little bit of review. So for proportion, we had the population proportion. And then we took a sample, and what did we get? We got not a P, we called this a P hat, right? We got the sample proportion, correct? And we concluded that this and this should be the same because they are an unbiased estimator, right? Okay. And then we had a standard deviation here, and then we had the sample standard deviation, but we said that the sample standard deviation would go like what? We said it would be this, correct?
Correct.
Right? We said this, so we didn't really need to know this. Right? I could, without knowing this, I could, as long as I got this guy, I could plug and chug in here, and I can derive this guy. Right? What are some of the conditions that had to be met? Had to be a random sample. Cannot oversample. No greater than 10%. Right? What else? Large counts. Yes, very good answer. Large counts, right? Actually, no, you guys, it was 5, right? 5, right? 5. I'm so used to using 10. 5. Okay, this was a large counts. Okay. So, for the mean, we're going to have just about the same thing. Just about the same thing. For the mean, it's no longer going to be this. It is this. Okay. And over here, instead of p hat, we're going to get an x bar, the sample mean. The sample mean. What are we going to do with this? We don't have a p or a q. Correct? So to exacerbate that problem, not only that, most of the time, we do not know this. Okay, we don't know what that is. So I have nothing to go with. Okay. Now what we have here is that we have a standard deviation of the sample. We do know that, right? Because when we take the sample, if I took a sample of, I don't know how many we took, like a sample of 50, I can just put it into L1 and I can get do the one bar stats, and I can get the standard deviation, right? So you're going to get a standard deviation, right? You just don't know what to do with it, right? Okay. So what we're going to end up using is we're going to end up using this. Okay. So we're going to end up using this. This stays the same. This stays the same. This can't be the same because I don't have any P's and Q's, right? Right? So the large counts for a mean is simply going to be this. Okay. Does anybody remember the significance of 30?
If your survey has more than 30, then it's like automatically normal.
Correct. It's automatic normal. And that was called the central limit theorem. Very good. All right? So if the sample, so remember we did this and we said, well, regardless of what this population distribution looks like, if I take more than 30, my sample is guaranteed to be a normal distribution. Okay? All right? As long as I take more than, so if my sample size is greater than 30, I can say that. Okay? So let's go to page 317. I'll go to page 317.
I finished taking my test.
So, sample, if you go there, we're on 317, look at the objective, look at the notation. We went through the notation, we did that, we talked about the requirements, we did that. Okay, the confidence interval is what? So if I do that, they said that the confidence interval is going to be plus or minus this guy. Right? Right? So that's the margin of error. Margin of error, you get E is equal to T alpha divided by 2 S divided by square root of N. So we are all familiar about this except for this guy. What the heck is this? Right? We learned when we were doing the proportions, we said it was not this, it was the, what was this here, the critical value? It was the Z value. Remember the Z value, right? Now here we have a T. Okay. And I'm not going to go through all the details, but the reason why we cannot use a normal distribution here is because we do not know this. Because we do not know this, we cannot use a normal distribution. We're going to use what is called the T distribution. Okay? T distribution looks like this. If this is a normal distribution, the T distribution looks like this. So it is a kind of like a normal distribution, but it has fatter tails. The tails are fatter than the normal distribution. Okay? If you go to the back of your book, there is a T distribution T table, and that is on page 686. Let's all go there. Page 686. It says T distribution. Okay, it says T distribution is kind of like the normal distribution. Look at the left side. There's our left tail, right tail, two tails. Critical T value instead of the critical Z value. Right? On the very first column, what does it say? It says degrees of freedom. What the heck is that? And this is the first time you guys are hearing this. Degrees of freedom, DF. Degrees of freedom is equal to the sample size minus 1. So if my sample size was 30, my degree of freedom would be what? 29. So if you go down that column, there's a 29. All right? And for 0.005, 0.01, 0.025, it has all these values for you. Right? So for a 5%, and for the degree of freedom of 29, it will be 1.699. Do you see how that's kind of similar to the 1.645 that we used? Right?
Yeah.
It's kind of similar, but it's a little higher. Again, because the tails are fatter. Okay? All right? So that is the thing that you would use there. So in other words, your critical value depends on your sample size. Okay? As the sample size goes up, your T distribution is going to go up, 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 and push closer and closer to a normal distribution. So the higher the N value, the T distribution gets closer and closer to a normal distribution. Okay? All right. So let's go to page. Oh, there's an interesting blurb there on page 318 that says student T distribution. Anna, read that for us.
In this section, use student T distribution, which is commonly referred to as a T distribution. It was developed by William Gossett, 1876 to 1973, who was a Guinness brewery employee who needed a distribution that could be used with small samples. The brewery prohibited publication of research results, but Gossett got around this by publishing under the student, strictly in the interest of better serving his readers. The author visited the Guinness brewery and felt obligated to sample something.
Nice.
Here are some key points about the student T distribution.
Okay, thank you. So this is kind of a side note, okay? So William Gossett worked for Guinness, right? And he was basically a statistician, right? So they did not have a T distribution at this time. If you look at the dates there, it's 1876 to 1937. This kind of shows how young or how green the statistics field itself is. It's only been around for about 100 years. Okay, it's a fairly recent field. Okay, so, but anyway, so the Guinness brewery said that you cannot publish this stuff. Why did they prohibit people from publishing stuff?
It wasn't vetted by you.
No. It was kind of like industrial espionage. It's their secrets. It's their trade secrets, right? They don't want that stuff going out, right? So they prohibited anybody from giving out data about how they made stuff and what they did and what based on what and all this stuff. Okay, so that's the background between the student T distribution, the naming of it. All right, just a little tidbit there. Okay, so let's go to page 320, example number 1, and see if we can actually do this. Okay. Find the critical value T alpha divided by 2 corresponding to a 95% confidence level given that the sample size was 15. So you go back to that table, and since the sample size was 15, what is my degree of freedom? 14. So let's go ahead and read the line where it says 14. And we are looking at a 95% confidence interval. So that would be what? 0.025, correct? Because it's going to be a two-tailed, right? 2.145. Everybody see where that 2.145 is? We're able to read that off? Okay, all right. Okay, so that's that. So now we know how to read that table, okay? And that's all we're going to do today.